This recording is one of a few early in the semester that serve two purposes. One of them is the sample calculation for the Unit 1 density lab, and the other one is for the Unit 1 lecture where I'm talking about significant figures, units, errors, qualitative, random versus systematic, the quantitative errors, computational. By the way, that will happen only here, that we talk about quantitative computational errors and outliers and median value. Okay, so anyway, just about get started. I'm going to use the data that I got in my sample density lab that I posted, do the calculations there, and I believe in this recording, as I posted on YouTube with a maximum of 10 minutes, I think I only have time for looking at significant figures, units, and just a little bit on errors. The actual error calculation and looking at the errors I'll do in another recording. Okay, let's get going. I used a sample, a cube of lead, and I looked up the density on the internet. It is posted as 11.35 grams per cubic centimeter. And now here's what I measured. 3.1 for the length, 3.1 for the width, 3.1 for the height, and 355 for the mass. And at this point I already got it wrong, and you would be marked wrong because any kind of measurement needs to take on a unit. So this is 355 grams. The height is 3.1 centimeters, and centimeters. In a video I said that I'm tried to measure this here as accurate to the closest half millimeter, so 0.05 centimeters, kind of in the divisions, in between the divisions of 3.1 to 3.2, kind of in the middle. So 0.05 centimeters. There we go, there we go. And then with the spring scale, I estimated that I was able to measure within plus minus 3 grams. And as I said, I will talk about the percentage error and how to calculate the error in a later recording. Okay, so at this point, let's figure out what the density is. The density is mass divided by volume. So I'm going to calculate the volume, which of course is length times width times height, and then I divide that into the mass. So let's get a calculator. 3.1 times 3.1 times 3.1 is 29.791. Of course, that could be a little bit faster if I did this. 3.1 cubed. There you go, same number. Now I divide this into 355. There we go. And I come up with 11.91 and so on. And on your lab sheet, it indeed says to write down the entire number from the calculator, so 11.91635058 grams per cubic centimeter. But of course, this is a total overkill. You're pretending that you measured this accurately. You did not. You measured 355, that's 3 significant figures. 3.1, 2 significant figures. 2 significant figures. 2 significant figures. And your result has to reflect that. The result cannot have more significant figures than the least of your measurements. And you have 2, 2, 2, and 3 significant figures, so your result can only have 2 significant figures. As I said, the least amount. So I'm gonna look at 1 and 1. That is 2 significant figures, and now in order to round correctly, because of the 0.9 here, it comes out to 12 is the correct answer. 12 grams per cubic centimeter. Notice that that is actually relatively close to 11.35, and we can figure out later why it's not exactly 11.35, why it's around at 12. Okay, let's do the next example. I used an irregular shaped specimen, and it's galena, which is lead ore, lead sulfide, for which I looked up the density as 7.4 grams per cubic centimeter. But here are my measurements. I measured 50 grams, and then I immersed it in water and measured 45 grams, and the reason is that when I immerse it in water, water is pushing up on it with its buoyant force, and so it appears that its weight or mass has decreased. I believe the word or the expression apparent immersed mass, I even got that from our textbook. The calculation for this one here is different. Again, I wasn't able to determine the volume of the irregular shaped one because it's hard to measure, so I use this different way of doing it. By the way, the error here, I believe I said in the video 2 grams and 2 grams, and again I do the error calculation itself actually later. Then I'm going to calculate mass divided by the difference between the two masses. I could just about do that in my head because the difference is 5, and I would have to divide that into 50. But let me show you on the calculator. So it's 50 grams divided by the difference between the two, 50 minus 45. Make sure you put parentheses around that if you do that in one step. And of course it comes out to 10. And actually it just comes out to 10 because grams would cancel, but what happens here is what I just actually calculated is specific gravity being 10 as it compares it to water, and the density of water is 1 gram per cubic centimeter. That's why it works. The specific gravity of water is also 1, and that's why the two are equivalent. So as I write here just a 10 because the units would cancel, that's actually equivalent to 10 grams per cubic centimeter. That's because I immersed it in water. So 10, I look at significant figures, and yeah, how many do I write down? Well, I measured to two significant figures, the 50 and the 40, so just the 10. Now somebody could argue, well, I subtracted actually these two numbers, 50 minus 45, which is 5, so actually I only calculated one significant figure. But I have to write this 0 down here anyway as a placeholder. So I could figure, well, is it significant or not? Well, that is discussed in when I talk about zeros in other recordings. Okay, so I come up here with 10 grams per cubic centimeter, and when you compare that to the book or internet value, that's 7.4. So I'm somewhat off, but I think I mentioned it in a video that I had quite an inaccurate measurement as I was trying to take, for example, the 45 and saying, wow, plus minus 2, that's already quite a bit, especially once I subtract these two. Okay, because I wanted to talk about significant figures and units in this one and reserve errors for the next recording, I'm done for right now.